Part 2, Quantum Theory and the Discovery of New Particles. At first, there was thought to only be 3 fundamental or indivisible particles. Those, of course, were the electron, the proton, and the neutron. Okay? However, as bubble and cloud chambers were developed and refined, more particles began to show up. The original 3 were not as fundamental as first was thought. Okay? So let's talk a little bit about antimatter. Okay? Antimatter is the opposite of matter, meaning it has one or more similar properties, such as mass, to its matter counterpart, but one significant difference. So usually it's charge or spin, something like that. For example, electrons and positrons are matter antimatter counterparts. So they are exactly the same mass, they just have different charge. An electron is negative, a positron is positive, but they weigh exactly the same amount, 9.11 times 10 to the negative 31 kilograms, etc., etc. So, when matter-antimatter counterparts interact, the process is known as annihilation, or basically the particles destroy each other, leaving 2 high-energy gamma particles traveling in opposite directions. It's important to note at this point that annihilations only happen when you have a matter-antimatter counterpart. So if you had an antiproton and a neutron, antiproton is antimatter and a neutron is matter, but if they collide, they won't annihilate each other because they're not a pair. An antiproton and a proton, on the other hand, if they collided with each other, they would annihilate each other. So it's not just matter and antimatter, it's the matter-antimatter pair. So, why 2 particles? Why wouldn't they just make 1 particle? Well, the answer to that goes back to the fundamentals of physics. Conservation of energy. That's an R. Of energy. And momentum. So the thing is, what ends up happening is the 2 masses, what happens to the mass? You got to have conservation of mass, right? But as we saw last unit with Einstein and the mass, energy, and mass equivalence, the mass of the matter-antimatter counterparts, the mass all gets converted into energy by E equals mc squared. So the 2 photons, all the mass of the particles turn into the photons, the energy. So that's conservation of energy. Great, yay. Now, the thing is, though, remember from back in EMR, we know that photons have momentum. So if you just had 1 photon, that would mean all the momentum is going in one direction. But if you have, let's say, an electron and a positron, right? That'd be an anti-electron, basically. Or I guess it's positive, right? If they annihilate each other, look, there's momentum going this way and momentum going that way. Now, if their momentum is still 0, how do you make 1 photon, going this way? Wait a sec, because that would have momentum going up. Now again, it doesn't really matter left, right, up, down. It's fine because the total momentum is going to be 0. But the thing is, if you just have 1 photon going this way, it has momentum as well. So wait a sec, the momentum wouldn't equal 0. So you have to have 2 photons going in opposite directions to balance out and have conservation of momentum. So it has to be 2 particles, 2 photons. Awesome. Some theory for you, yay. Now we're going to talk about mediating particles. So these are virtual particles that carry or make or responsible for the fundamental forces. Remember, there's only 4 that scientists have figured out. Okay, remember those four? That's the electromagnetic force. Okay, so that's electric forces, magnetic forces. Okay, the weak nuclear force, the strong nuclear force, and the gravitational forces. Only the four forces. Okay, so these virtual particles are responsible or make these forces. They are considered to be virtual because they only exist for such a short period of time that they're practically not there. Okay, the following table lists the fundamental forces with their mediating particles. Okay, so electromagnetic forces, okay, they are mediated by photons. Okay, they have an infinite range, okay, and the relative strength for protons in the nucleus. So relative strength is just how strong is it compared to the others. Okay, so this is like 10 to the negative 2. So, you know, not crazy. Like 10 to the negative 2 is 0.01. Okay, like 1/100 sort of thing. Okay, so not strong, not weak, all good. Okay, and have we observed these particles? Yes, of course we have observed photons. Okay, the weak nuclear force, on the other hand, okay, the range for that is 0.003 femtometers. Now, if you remember femto on your formula sheet, okay, on your back of your formula sheet, femto is 10 to the negative 15. Like very, very small. Okay, so anyways, so the weak nuclear force, the things have to be very, very close together for the weak nuclear force to make any difference. Okay, the relative strength for protons is 10 to the negative 6, so that is not very strong, certainly not as strong as the electromagnetic force. Okay, so there are 3 mediating particles for that, W plus, W negative, and Z0. Okay, have we observed those? Yes, we have. Is it important that you memorize this chart? No, but just remember, this is where physics is going, so just bear with it. Okay, so the strong nuclear force, okay, that is less than 1 femtometer. Okay, the relative strength for protons is 1, so that the strong nuclear force is extremely strong. Okay, that's what holds the protons and neutrons together in a nucleus, remember. Okay, so their mediating particle is called a gluon. Okay, and we have not seen them, but we have indirectly observed their effects. Okay, and then of course gravitational forces. Okay, they have an infinite range. The relative strength for protons 10 to the negative 38. Wow, that is so incredibly small. Okay, remember gravity is a very, very weak force. Okay, their mediating particles, scientists are calling a graviton, and no, we haven't seen that yet. Okay, they are guessing that it exists. They know it exists because the other mediating particles, the other forces have mediating particles, but scientists have not seen evidence of them yet. Okay, so wow, lots of theory. See the short little video, but lots of theory in it. Okay, I want you to practice this by doing questions 17.2, starting on page 839. So I'd like you to look at 1, 3, 6, and 8. Again, good luck. You might feel the need to read the whole section, 17.2. Please feel free. Do those questions. We'll see you next video. Thanks.